A seat, please. We have a busy and very rich and exciting schedule. If somebody give me some sound. Shall I try again? Am I on?
Yes, you're on.
Okay. Thank you. Right. We have the keynote speech by Professor Bignou, whom I'm going to introduce in a few minutes. Before that, we are very happy to briefly have some remarks from our very own Professor Sabina Nuti, Rector of the Scuola Superiore Sant'Anna, who doesn't really need a long introduction here, but I think she's going to mention very briefly some of the key aspects of her research for us. Sabina, the floor is yours.
Thank you. So thank you very much. I'm really very happy to be here today. As I think most of the people here in the room know, I was elected in the role of as a rector in May, and my life completely changed. So it's very nice for me to have some opportunities to go back and to open my head, my brain to the research topics. And so I'm really happy to be here to introduce the day. First of all, I would like to thank Francesca Chiaromonte and all the team of our professor joined the two Institute of Economics and Management for working together. I think this department it's a success, first of all, because we've put together two different institutes, and we started to work as a joint team, and I think this is really important. I was in the last days with the minister and with all his staff, and we discussed a lot on how it's important for the future of our country to carry out research with an interdisciplinary approach. And I think this excellent department are a good example of what we can do. So thanks for organizing these 2 days of meeting, and thanks for putting together people with different perspective and approach to discuss about big data and the impact that this can have in our lives and our society. When Francesca asked me to introduce the day, I thought, well, shall I speak as a rector or shall I speak as a health professor as a professor working on healthcare? And I thought, I'd do the second part. I like it much more, and I would like to give some, just a couple of suggestions of what does this mean in our work, considering the research team of the MES lab inside the school. Well, this topic, the era of big data and what does it mean for the healthcare system, is one of the main topics we have to speak about in our management training courses for policymakers and for managers of the healthcare system. And usually when I start my class on this, I start with this video. So, big question. When do you think that Microsoft did this video? Tell me, when? When you think they did this video?
10 years ago?
5 years ago?
5 years.
10? It was done in 2006. And when I say this to the managers in the healthcare system, they can't believe it. Because they see this video and they say, well, go on, this is going to be in place in 20 years, in 30 years. They did this in 2006. They were able to think of what is going to be the future for today. And so this is a first very important consideration. We, in our society, and I'm speaking about especially the healthcare system, the people working in the system are not able to understand what's going to be the revolution. You know, they think that what was presented in this video, it's a challenge that's starting now. Instead, somebody in 2006 was able to design could be the future of the system. So I think this is a first important suggestion that we have to keep in count. You know, we are speaking about big data. We know that it's going to be a revolution, but we are living in a society that doesn't even have an idea of what is going to happen and how technology and how big data will change our life. When I speak with clinicians or with policymakers in the healthcare system, they tell me, well, our patients, most of them, 80, 90% are old people. And old people don't use new technologies. They don't get connected in the internet. Now, these are the data that were presented last year for United States, and you see that people over 70 years old, in the majority of the cases, they already use internet, they are online, and they stay quite a lot on internet. And these are the data of Italy, 2019, and you see that not as much as the United States, but we have really a lot increasing the number of old people that use these type of devices and that are online. And so population is changing, people are asking more, usually we have some data very interesting that when people retired and think, I speak this for the Italians in the room, think about quota 100. If they retire, and they retire quite early, what do they do until the 75, 80 years? They start to work on these new devices because they have a lot of time. And so we have a lot of examples of people that never had time before, and suddenly they retire and they learn. And so they start to stay really a lot on internet. I go quick on this, I don't want to lose time, but look, this is the last data that we have on this, and you see that people over 65 stay about 3 hours a day, you know, on internet. So people are starting to get used to be in touch and to use these type of devices. And we know that putting together all these different fonts, we can really put in place a new way of caring for people, caring for patients. Think about personal assistants and smartphones and mobile application. We are full of new ideas and new application. And please consider that these type of solutions were designed from outside the healthcare system, not from inside. And so this is an important issue. Just a few days ago, we had this impressive presentation of Google Health and what Google can do in predicting medical events. And then this seems really a new challenge. And with my colleagues in the MES lab, research lab, we start to ask ourselves, is it another promise like the ones of the 2006 of Microsoft and the video clip that you saw at the beginning of my short presentation? Well, this seems really a revolution. We know that the healthcare system since about 20 years is working to putting together the data regarding each patient and connecting different source of data. And we are still there with a lot of problems and spending a lot of money. And now we have somebody outside the system with a very step forward approach, very aggressive, that is going to be part of the system and is going to be very difficult to keep in count. A lot of elements are quite relevant in healthcare, like privacy or like protecting data, very sensible, like the one regarding the illness of our patients. So this is going to be a big challenge. And look what we are doing in our research lab. Perhaps yesterday you spoke about this. I was just thinking that in the last 8 months of 2019, we contacted 50,000 patients. We got 20,000 questionnaires. We had more than 200,000 free text comments. Well, this was not possible a few years ago until I think a couple of years ago. I looked, Sabina De Rosis that's in the room here, and she is the expert about this. We were using traditional surveys. So written surveys, we need to receive these questionnaires about 6 months to have the sample and to provide reports after more or less 1 year. And now, in few months, we have an incredible amount of data. And the big question is, what are we going to do with all these data? How are we going to use them in the best way? How are we going to make the difference from a research point of view, but also from what we call third mission? How are we going to do something for citizens, for population, and for policymakers, so that this great amount of data can become good ideas and suggestions to improve our healthcare system? So I think we have a big work to do inside this department and in collaborating all with other researchers about these issues. So at the end, this is my last slide. This is what we put in our strategic plan for the next years. And this is going to be very synthetic way what is going to be our mission: to be a research university, first of all, so with really good results in the research production, but joined to a role in our world and in our society, so a school of talent for a more sustainable and inclusive world. I think we have to keep in mind this type of mission and think also regarding all the big issue regarding big data. How are we going to use all this information and how we can really do the difference for our society and for our university, for our students, and for all the research world. So thank you for being here. Welcome to the school, and I hope that you can, working together, we can have some more results to share with all the scientific community. And thank you.
Thank you very much, Sabina. Now, it is time for me to introduce our distinguished guest who is going to give today's keynote. Professor Binyu, who is here, is Chancellor's Professor of the Department of Statistics and the Department of Electrical Engineering and Computer Science at the University of California at Berkeley. She has a rich and highly articulated CV because I think she's fundamentally a very curious person. She leads an interdisciplinary research team that focuses on practice, algorithm, and theory of statistical machine learning and causal inference. She's done a lot of work applied to biomedical problems. Across projects, across papers, she addresses with colleagues at UC Berkeley and some of the other leading US universities and world leading universities, very difficult problems. She has a long list of awards and recognitions to her name. To name just a couple of them, she's a member of the US National Academy of Sciences and a fellow of the American Academy of Arts and Sciences. She was a Guggenheim Fellow, Tuckey Memorial Lecturer of the Merdunli Society, President of the Institute of Mathematical Statistics, and Reeds Lecturer of the same institute in 2016. More recently, she received the E.L. Scott Award from the Committee of Presidents of Statistical Societies. We already heard her speak yesterday. She gave a very interesting paper that highlighted some of her work on iterative random forests applied to biomedical problems. And today she is going to expand on three principles of data science. We have, with some abundance, 1 hour, 1 hour and a quarter, more or less, so that we have time for some questions. I would like to again express our warm welcome and our thanks for being here, and we look forward to your lecture.
Thank you. Thank you very much. Thank you for the rector for coming, and Andrea for the very kind introduction. So I think the name of vertical data science was just suggested by a colleague, Tian Zhan from Columbia University, when I was there 2 weeks ago, and for a trustworthy AI workshop. And she came out with his name after a discussion, and I had to look up the dictionary, so I'll do the same for you. So it's a Latin kind of root word, meaning truthful and coinciding with reality. And after vetted by my group, we decided to change the name. So I talked to my group, and they liked the name, and they said I shouldn't change the PCS. So I listened to my students, and we changed. So as Andrea alluded to in yesterday's talk, most of my projects right now are biomedical problems. UC Berkeley had a AI for biomedicine in June, and we have a project I mentioned from BioHub, which will end up with single-cell experiments with inter-repositories, and the Google has this protein folding AlphaFold, and a very interesting work from Suchi Saria from Johns Hopkins, kind of healthcare, which the rector spoke about related to her work, right? So all these things underneath the hood is data modeling, right? All of this with all the fancy interface, but somewhere there's data and decision to be made, hopefully jointly with human and data modeling. So to make a connection with this group, I made an effort to think about economics problems. The easy ones for a bank is how do you predict the probability of default for a credit card applicant? And can you estimate customers' value based on flow models and basic policies and economic factors? And I know a lot of people here work on patent data, and we're starting some engagement with Lee Fleming at Berkeley, look at US patent data to see whether you can predict high growth. I learned it's a hard problem last night. And also something I will return to about predicting growth rate from public debt and GDP ratio, which a particular famous paper by Reinhardt and Riegel that are really behind a lot of austerity policies in Europe. So what's data science, right? Big data and data science. So there's this nice Venn diagram, computer science, math and stats, and domain knowledge. and the intersection is data science. It's very hard for somebody called data scientist to be able to cover all three. But as a team, I think we need to cover all three. And machine learning has emerged as a very important interface, discipline field between computer science and math stats. And the Berkeley definition of data science is really try to bring computational and statistical thinking together in the context of domain problems. A bit history. Around 1890, there was a statistician called Herman Hattaway working for US Census. That year it was predicted it would take 13 years to finish the census processing. And he was charged to speed things up. As a result, he became kind of a computer scientist. He devised this Hattaway's tabulating machine, and it's in all the computing museums, and they took only 6 months. And then we have Fisher, right, a bit later, who is really the founding father of modern statistics, and he was never a professor of statistics at Cambridge. He was a professor of genetics. So the science was always there. And if you look at the data science life cycle, I like to see it as a system, not disjoint parts. It's a system beautifully drawn by my student, Rebecca, and we make so many judgment calls. That's what I want to bring out. In there, from the question formulation, what data are you going to use, you're going to collect? How are you going to clean it, right? All the data, the rector mentioned that, these surveys, it's known as survey data, very noisy, have a lot of measure, and how much they're really telling you what they do. How can you deal with missing data? All of that is and put under data cleaning. In my team, data cleaning easily take 80% of our effort, and we rarely talk about it in any talks. We pretend it's not there. I don't think we can. I sometimes have this worst nightmare of fear that one day I'll be killed by my own algorithm. Because my algorithms are out there. There's no label, nothing. Somebody can use it and treat me and my children. And I don't feel very good about that. Even we try to vet our algorithms. We need to have labels and things like that to help people to use the algorithm rightly. And we don't. So I'm not blaming anyone, I'll blame myself. So that's what I'm trying to do. I think I'll be happier dying if I do something and I still get killed by my own algorithm. But that's something to keep. It's different using machine learning for revenue. This is human life, and you cannot just say, average, we did well. You want every case. You don't want to harm anyone. This is a very, very different arena we're entering. I don't think people really realize that. It's really underneath all that beautiful Microsoft video from 13 years ago is what Bill Gates called danger. Right? Bill Gates recently said that AI is like energy, nuclear energy. It has great promise, something like that, and also it's dangerous. Right? It's one of those things have huge potential, but could also hugely harmful if we're not careful. So that's in the spirit. I want us to see this as a whole system, right? And then you have modeling algorithm. We spend most of our effort here, which is not really justified. With reliable software, this effort can be actually automated a lot better. But other things, how are you going to interpret which part, which plot are you going to use? How are you going to start the circle again? It's human judgment call, let's face it. It's not objective in the sense of always reproducible. So here's an attempt to define vertical data science. What I was talking about, the three principles of data science, is effort towards this goal. It's a big name, but I think we can together go there, at least toward there. I don't claim we're there yet. So we define vertical data science as direct, reliable, reproducible information from data, and also with an enriched technical language to communicate and evaluate empirical evidence in the context of human decisions and domain knowledge. So there's human engagement. It's not just some symbols. We sometimes hide too much behind symbols. Symbols have no meaning if it doesn't have correspondence with reality. And we don't talk too much about it. We quickly, I taught for 25 years, it's no longer, start with X in my first lecture. Right, so I'm just as skilled. But I think we have to change that, especially more and more people going to enter the field. And what does X mean? We need to spend more time answering that. For the rest of the talk, I'll introduce the PCS framework for vertical data science. And I'll do 2 case studies, the second one pretty briefly. This is kind of 2 parts of a long-term collaboration with J. Galan's lab, lasted now almost 15 years. And the second part used deep learning, so I'll mention a bit on that. And we have like 18 different predictive models, how we can do interpretation. And then I'll try to pretend to know a little bit economics to do a discussion on Reinhardt and Rogoff, and hope that the audience will join me and be the expert really. Okay, so the 3 principles of data science now, we have the acronym PCS, predictability, computability, and stability. And in one slide, we're finishing a paper with my student, who now a postdoc at UCSF, on the 3 principles. So P and C really is building on machine learning. Statistics always did predictability, but we never put computability at the center as machine learning did. And then we add statistical consideration in a much expanded manner, from sample to sample variability to about problem formulation, data cleaning, all the other decisions we make along the way. And Rebecca made this beautiful drawing of the PCS tree. Stability is the roots we stabilize, and we observe nutrients from data. Computability is the trunk. Without computability, the tree will fall. Without root either, and then we have results that like predictability, can be inference and other things as the fruits. And PCS also connects science and engineering, right? Predictability and stability really embodies 2 important scientific principles, prediction and replication, right? I was trying to make a connection with this Galileo Galilei's work, right? Definitely he was into prediction, and he was also, I think people replicated this supposed experiment he did on top of the Pisa Tower to see that the acceleration doesn't depend on the weight. And there was definitely a Dutch replication, right? So for science, we need this replication. And stability is like human judgment calls. We have to have some replication instead of, oh, one person did it, you have your science, and another person, Professor X has a sign, Professor Y has a different sign, they're all in statistics. So that's very disconcerting. And computability, not just, oops, what did I do? Oh, good, coming back. Not just about scalability and data storage, database, the traditional computer science. I think if you really think about computability, it's all about data-inspired simulations. And that's something I think is underutilized in chemistry, biophysics. They do very serious simulations. And we don't. We need to do more to really understand misspecified models. We do too much under the ideal model. So I started working on stability, actually, as Andrea mentioned, as part of the Bernoulli's Tukey lecture. It was delivered 2012. And the paper appeared in the special issue of Bernoulli 2013. So at that time, I was very concerned about interpretability and reproducibility. There was a lot of popular media coverage of false discoveries in biology. And later, since my interest moved, also includes the causal inference, it's also become part of consideration for scientific hypothesis generation or intervention design. So stability, it's a very common sense principle, I'll say. I asked a philosopher friend, Brandon Fossen, that somebody smarter than me must have said something. And he said, yes, Plato has something. So he gave me a translation, part of a dialogue manual. It says something like, knowledge has to be tied down, unlike opinions that can change day to day. So it's like knowledge, that's what I hope we are going after, it's stable. The referee didn't like it, so we removed it, but I still like it. And stability really is like shaking the system so that it doesn't break and you have a better product. The shaking really comes from the human decisions, right? Everybody does these different parts a little differently. When you change the different parts, you still get a reliable system, and that's a good system. It doesn't mean that it will never break, but it's a much better product than you don't shake it at all. So think about stability is about shaking, and we want robustness. The reason I didn't use robustness because robust statistics tend to have a narrow focus. And the workflow is really taking the whole system and incorporates both predictability, computability, and stability into each step. Predictability is very clear at the modeling step. That's where machine learning is. But I want to push it also upstream to domain problem formulation. So I interpret predictability as a general about the future. If there's no future, I should stop my talk and go home or do something. So everything's about the future. We never do the data work because there's no future. It's all about the future. So in that sense, predictability is everywhere. And also about data cleaning, data collection. It's also about, I'm collecting this data. What other data might come along? You should always keep the future suitability in your mind. Also data cleaning. Somebody else come tomorrow. I have a new group member. Will he clean the data the same way? So it's always thinking ahead. So that's what I think predictability is relevant. And stability. For modeling, it's about data perturbation and model perturbation. But for data cleaning, I have 2 students who clean the data. Will we get the same result? Another lab clean the data. So I know that RNA-seq, which is a major form of genomics data now, have 2 standard procedures to do data pre-processing. Would you get the same result? Usually people choose one and go ahead and build whatever models. Would you get the same result? If not, do you want to be treated for cancer prediction based on one processing and not the other? The reason both are popular, probably some people like one, some people like the other, because there's no clear distinction, then shouldn't you try both? So that's also a form of stability, which is very hard to put under probabilistic models. But it's a perturbation. So perturbation and shaking are the same thing in my talk. And linguistic stability about problem formulation. I had a chance to have dinner with a very well-known breast cancer researcher from Berkeley Lawrence Lab. And she developed a theory called the microenvironment, based 30 years ago, seeing cancer as an organ, not just disorganized cells. It took 30 years for the field to accept it, but now people are really embracing it. And she has something called a matrix to describe the biological structure. You know what I mean for most people what matrix means. So over dinner, I tried to tell her that my matrix was different from her matrix. It didn't come across. Of course, I didn't insist. So if I end up working with her, that means we have to, when we mention matrix, we only have to say matrix A versus matrix B, because it means 2 different things. And people come from different units, might not understand the same words in the same way. So right there, you need linguistic stability. And language stability actually means computing platforms, codes will run. So you need that too. The code will run the same way over different computing platforms. So that's called language stability. So all of that, stability, every step, there's a human decision. Bootstrap versus self-sampling, why don't we do both? Right, as simple as that. So all of this, you have forking all the paths. You should at least try a few instead of just one. And with every decision kind of arbitrary, a bit arbitrary made. And we also develop basic, because we want to do forward inference, is try to expand on statistical inference. To talk about perturbations at the cleaning stage, problem formulation stage. You want to see whether gene 1 is important, a transcription factor. Say Zelda as a target is important. If you use random forest or iterate random forest, would you get the same result if you use lasso? Why? Which one do you use? So all of these questions can be put data perturbations or shaking. So this is more traditional ones, right? We're familiar with. Usually need kind of at some level ID assumption, or at least things exchangeable and independent. And the more recent ones, you have proteomics data, you have genomics data, you have all kinds of data. Which one going to use? And how do we incorporate PDE-driven models through synthetic data, right? Yesterday there was a talk, I think Simon, on using PDE models. Maybe you can put them together and do it just as data instead of putting them as mean functions in a stochastic model. Because this way you don't need to write another line of code. And invariance under different environments have been used for causality and differential privacy. US Census is going to go for it. It's a form of stability. And adverse attack to deep learning models. It's also a form of extreme perturbation. And You can easily switch the medical imaging diagnosis by adding some noise. Healthy become diseased very easily, right? Do we want to be one of those? And also, people can game it. Say, insurance company can try to game it by hacking into a medical database and start switching everything. And then the AI algorithm will start just making wrong calls for whatever. Right, so all these things make the system as nicely, beautifully portrayed in the Microsoft video. Underneath, there's a lot of instability, or we want to remove the instability as much as we can. And the one I did it for this audience, let's see how you like it. It's also data cleaning. This is a well-known case that there was a New Yorker article about 10 years ago talking about the Reinhardt and Rogoff controversy. So there was this paper in an economic journal, I think American Economic Review, called Growth in a Time of Doubt. Two Harvard professors who made a claim that if the public debt over GDP ratio is over 90%, you see a drop of growth. And therefore, that has been used for austerity policies. And this is the data clean matter. They deleted New Zealand, who had very negative growth rate. I think which way it goes. I know they deleted New Zealand, and probably it goes the other way. They only use 1 year, I think, from New Zealand, and the other years are more positive. And with no explanation, no documentation why they did that. And after you bring New Zealand back, then the rate change become positive. So there was a follow-up paper to critique this paper we'll get to, and this was widely cited and very well known in the public domain. So we need to call stability, and as this Herden, Ash, and Pauline from Amherst show that if you do a different data cleaning, and there was also coding error, and they did some unconventional weighting, I think it's not as changing the result, then you have a different conclusion. I'll come back to that. And also about model perturbation, robust statistics. That's why I start putting data and algorithm perturbation together. Semi-parametric, all of these things that people make choices. For supervised learning, it's almost like, except for the first one, you can use all of them. Would you get the same result? Oh, you have researcher perturbation. Wonder whether Francisca will do the same thing in two versions of her. My guess is probably not exactly. I don't know how old was she at the time. She can tell you. I won't ask. Right? And team-to-team variations, right? We have 9 climate models by 9 teams of scientists, and we have a range. So this is something, a lot of time, because some people like their model, but for science, that's really weird, right? Depends on the team. You have a different science. And how do we claim objectivity? It doesn't mean we agree it's objective, but it's definitely not quite objective. You have 9 teams get very different, or 2 versions of you do different things. So all the things we try pretend not there. So all the things I list is human judgment call. This is actually from a Toronto for Kids site. We're supposed to have maturity already when we're adult. I don't think we're exactly there. Right, so I'm just saying that we also make judgment calls, sometimes good, sometimes bad. Hopefully we do better on average than teenagers, but I don't think there's complete analysis of that. So how do we really help us to trust what we do? One suggestion we have in PCI is documentation. So here you have reality, and you have models. The models are really mental constructs. They're not real until you build a bridge. Is there a bridge there? Everybody gonna say, you hope so. But we actually cannot see it. We assume because we saw Golden Bay, the 2 poles. So you have to build a bridge. You have to have quantitative and qualitative narratives. in your documentation R Markdown or Jupyter Notebook, and you put it on GitHub. This putting out serves two purposes. Writing it makes you more rigorous, unless you want to be fraudulent to start with. Most people aren't. It's because writing helped you to think. And putting on GitHub, just human nature. When somebody might be looking over your shoulder, you're more rigorous. Otherwise, you rush. We can just have a depository of this GitHub, like documentation, PCA documentation. And we can have an organization or someone can randomly select and have some referees take a look. Just the fact that it can be looked at, people are more rigorous. I'm now I try to make this implement in my group. Everybody will write the documentation. So we're just starting that now, and for my class. Otherwise, we have a broken house, right? The foundations are cracked, and you can imagine when the app, as cute as it may be, tell you to do something, would you trust it? Right, I got a garment recently, and I don't always trust it, right? So quickly, I was a slave for 3 days, and I started ignoring it. Because I don't really know exactly how they process it, and maybe it will be in the future even be more reliable. And people ask me, how do you choose perturbations in PCS? You can never consider all possible perturbations. You end up doing nothing. But if you pledge to a stability principle, then if you use too many, you only look for stable, consistent results, you might end up with nothing. So that encourages you to think carefully what are the perturbations are appropriate. And you make an argument in the documentation. So this is really try to bring some liberal art, persuasive narrative into the consideration. I think economics always had two sides. Let's really bring data science a bit like that. This link between reality and symbols cannot be made by more symbols. It has to be explained in natural language. And humans have to be convinced. You're not convincing a machine. Your colleagues have to be convinced the assumptions you made, like in causal inference, are legitimate or valid. And you document. So this is kind of presenting the research, the reverse chronological order. All the things I just said is really a distillation of what the project we have been doing now, I'm telling you. Right? It really came from we're practicing adding stability after my 2013 paper into statistical and machine learning practices. Then we arrive at this principle. So now I'm telling the motivating example. It's kind of old work, was appeared 2011, but it's kind of where I started, and it's very easy to explain. So it's really, that's where I started going down the path of stability. So this is a joint project with Galan's lab. I've been working with them since 2006, and we have only third paper still being written. So it's a very slow collaboration and very rigorous. I'll tell you later about the next paper. So it appeared in Current Biology, and the lead was Shinji Nishimoto, a postdoc in Jack's lab, who returned to Japan and had his own company. The lead from my group, Yuval Benjamini, returned to Hebrew University in Jerusalem. So this is what got a lot of sensation in the media. I don't know why it's shaking, but it's not supposed to be shaking. So it might be a transfer from Apple to Microsoft. Instability. Shaking it, right? I don't want this to shake, but it shakes. So you can see that we captured something, the media was really interested. We got into the Time magazine, called one of the inventions of the 50 top inventions, and Jack was all over Twitter. I even got some calls. I never appeared, and so Jack did it. And we lost the edible campfire in the list. I don't know why, but they called us a mind reading machines or something. So what's behind the movie reconstruction? So let's go back to these squares, right? And especially Italian scientist Piazza, right? So the story of Cyrus' discovery has 3 names: Piazza, Gauss, and Kepler. So 1801, Piazza observed Cyrus. He had 3 sightings with time elapsed and locations on the sky. That's the data. And I really love that time, right? That's probably he was everything, right? He was a priest, mathematician, astronomer. I think we're returning to that age. And Gauss was everything. I think he can be in 10, 15, 20 departments if he lives today. Another polymath. And Kepler was a German mathematician, also have 3 titles, right? I don't know about the astrologer part, but he at least have 2 reputable titles. And if you look at what Gauss did, he was really using a calculation to do these squares. And he used Kepler's second law of planetary motion, which says that the circular area swept out by an orbit are proportional to elapsed times. He first used some triangle different geometry, not differential, just plain geometry, and did calculation, matched observation, doesn't match, he went back, did better approximation. So it's really a numerical method to do these squares. So that's what we use in today's time, right? Right, more offensively. How this square works is because when things are nice, when you have a nice curved ball-like surface in 2 dimensions, if you have a data general mechanism, your estimates just hover around in the right location. So they really form a team data science, right? They have scientists, they have data collection, and they have mathematician data science type. It's really a team, just like today. Now we have the era of big data, which is the title of today, AI and interdependent research. And 2013, there was a US report taking mathematical science really to get into the domain areas. And recently, I was part of a workshop report by NSF called Statistics at the Crossroads, Who is for the Challenge? And really saying statistics need to focus on practice. So if you Google that, you're going to find the report. So both really sending the message, we need to go back to the problems. And BRAIN initiative, 2013, was a big deal. Francis Collins, NIH had, and Obama had a press conference. So neuroscience, kind of the new genomics. Actually, neuroscience also uses genomics now. And the brain signal are citing of Cyrus, and we try to do a prediction algorithm and do an inverse problem. So a very basic vision science. So when the photons from the light hit the retina sends a signal to relay back to the cortex. And the first area of cortex is called V1. This is the pathway called the word pathway. So we have 2 main pathways to forward information. There's also a feedback loop that this is the what. We decide what we're looking at. There's also a where pathway. And then V2 is similar, and V4. V4 I'll return to for the second project. It's much more elusive. So today, instead of one Piazza, we have a lab that collected data. It's a collective effort. People collected data under fMRI machine, which is a non-invasive indirect recording technique. And each voxel has hundreds and thousands of neurons. So it's not just a single neuron, but we bootstrap up because neurons seem to have similar functionalities when they are next to each other. And that's where the data came from. There are 3 subjects, have input movie clips from YouTube and movie trailers, and measure corresponding fMRI. That's where a lot of judgment calls were made. They did 2 hours. That's the starting point of my stability. It's like, why 2 hours? Why not an hour, 15 minutes? If I do that, I use the soup because we do a Cabal Transform first. I get different selected variables. So that's the beginning of the stability thought, which actually is project. I want to interpret. So here's the data. Again, it's shaking. I don't know why. But it's an instability. Yeah, on my Mac, doesn't shake. So you can see that we have very little patience. So when this is process data with some systematic trend removed. When it's blue, that means we get bored. We get bored actually very quickly. We don't have a lot of patience because we do prediction. When we can predict well, we don't spend energy to care. And we're really excited about fire. With the shaking, fire doesn't look as exciting anymore because fire is the shake by itself, but now it's the added shaking. Everything looks like a fire now, but this one doesn't respond to that. I'll let you see the fire, I'll move on. Where's the fire? Yeah. Now you cannot tell. Everything is shaking. So the fire excites us most. Maybe it's because of danger. So what's V1? V1 has been figured out by 2 Nobel laureates. Among other things, they decide to have a sleepy cat and pop the eyelids and let the cat eye see the signals. So what you hear are the sounds from neuron firing, and they basically induce causality. When the stimuli is at a particular location, they induce in causality. So this neuron cares about this particular location. They also figured out there's also orientation selectivity and excitatory and inhibitory regions. And the modern way describing their work, is through something called the Cabal filters. So we can make Cabal filters very nice, great spatial frequency, location, orientation, and we can mathematically have a reproducible way of processing it. Right? This is a way to really say there's a mathematical correspondence. There was very nice work by Bruno Auhaus and David Field, who discovered similar things through something called dictionary learning. It's kind of the first layer of deep learning. And you can do this Cabal transform and do compressive transform, and you end up with like 10,000 dimensions. When we have a movie, you can add a dimension and have a 3D Cabal transform called energy model. And we end up with 26 dimension. So this is just says that what we do in a more complicated way. So in the end, the pre-processed data, we didn't do the data cleaning. This is done by Jack's lab. So the question is, if you reprocess it, would you get the same thing? More or less, I think, hopefully they do, but we didn't do that. So we have a 26 dimension to do prediction, and we have only like 7,000 observations. You cannot do these squares because these square has too many solutions. So we come in with Jack's lab being the collective Gauss. And there's 2 terms called encoding from stimuli to brain signal and decoding going back. So we're doing decoding, movie reconstruction. Mathematically, you can say that there's enough neuroscience to say after the Cabal transform, linear model works pretty well. At a single neuron level, so for voxels, we believe it works too. We hope. And you have a yield-post problem. When you have very collinear, in high dimension, everything's collinear, when n is larger than p. But in low dimension, you can create a problem by designing 2 vectors very highly linearly correlated. You still see this many solution kind of thing. There's a ridge. And how do you fix the problem? In general, you basically just have to live with all these different solutions. But Cabal and Wiesel's work really suggests that even we have this high dimension, you have very small number of Cabal filters at the right location. That's important. Basically, lasso type of sparse problem. You have many, many things. You don't know which ones, but the important actors are a small number. So we did something like lasso and use cross correlation. So it doesn't completely solve the problem, but you can see it really ease the problem because lasso can also end up with non-sparse solutions. Right? So this is basically saying that it really helps. Use lasso, especially. And we show that with 2D model. So lighter, that means overall, we have each voxel a different prediction. So this is correlation. We have a better model because these sides all light up. And we only use, you can see, I only show you V2, V1 and V2, no V4, which I'll return to for the second project. V4, we don't have good forward. We didn't have good forward model, so we didn't use data for reconstruction, even when we had the data. And also if we just use like a generalized inverse to do the regression, that's one way to deal with it. It's the wrong constraint. That's really minimize the L2 of the coefficients. So you need to minimize to L1. You can see also light up better, which means overall we do better with sparse regression. How did we reconstruct? we use a huge database, which was not possible before the IT age. We've kind of used the database as our internal memory. So we use the lasso model after the Cabal Transform to predict. You observe something in the brain signal, you just predict 1,000,000 of them into the space of the signals, and you find the closest. And we took the average of the top 100. The weighting was a little sophisticated, but was not that hard. Okay, that's how we reconstruct the movie. Still shakes. So after the Cabal, that's the key. You say, well, that's trivial. No, the Cabal, 3D Cabal, that was the feature engineering, that was the hardest part. After that, it was pretty standard. But as I said, I wanted to interpret. You look at, because each Cabal is associated with a location. I was thinking that, how can we prove these locations are driving the fMRI signal, particular voxel? We can do animations of movies at those locations, see what happens. So I thought lasso maybe tell me the location. But if you look at lasso, you remove 10 minutes of the data, it tell you different locations. So that's two things. Look at the first one. If you look at, remember each Cabal, each filter has a location. That's what I plotted with blue. It really says that voxel A cares, this is make a grid, that's why it looks like grid, because we shrinked, we downsampled. It says all over the place, and it's not very reasonable. It's also going to take a lot of time. So we decided to add stability, because that's the first idea of stability behind the paper 2013, was really that I'm only going to look at location when I do some bootstrap or some cross-validation, the locations stay. If you do that, you actually shrink the possible locations much, much better to a reasonable neighborhood. And you don't lose predictive accuracy. How we did it was very simple. Build on cross-validation. You look at the predictive values for each fold, and you do a grand average. And you do something like reciprocal attached statistics. You want to see whether this grand average of linear regression function ratio, this is like a variance, is big or not. If the reverse is big, that means it's not stable. So you want this to be small. It's really tried to do almost like a test statistic, use some jackknife. For why we're struggling? Because we didn't use cross-validation. We just look for stability for that metric. And down us, you need predictability first. So all the ingredients of PCS we see in this work, we didn't realize that. It took us a long time, and Ching Wei, who's returned to National University of Singapore, was really good, persistent, instead of ditching the project. Another student could have just ditched the project. And he actually proposed the state. I said, let's go for beta, it's just not stable. It doesn't matter what you do, you have to project on the X beta before you see some stability. That was his idea. So what we did is that you start with a good model, predictive model, cross-validation. You find the lambda. And then just increase the lambda to make the model smaller to minimize the new metric. So you're really piggybacking on top of cross-validation. And we don't lose much predictive accuracy, like 1.3%, and you reduce the model size on average by 60%. So this one, it's a win-win situation. You don't lose predictive accuracy, you get better model to interpret. So we're doing really stability, right? We're not doing formal inference. And there was also stability in model selection by Manhausen and Billman, but they still have a tuning metric. What we like by ESCV is that we don't have any further tuning parameter. So we want to do a formal statistical inference in an expanded way we call PCS inference. I really feel working with scientists, we don't really have the power, or we should think we should have the power to make a decision for them. Say, p-value less than something, do this. I just don't think we have that. So it's really providing one source of evidence. And we really want to provide the evidence in a transparent manner so they can understand as much as possible how we reach the conclusion. And traditional p-value has been used as evidence for decision, but it's very problematic. And psychology journals just banned it. to code UL deepening is really not p-value's fault. We should really, I like confidence intervals at UL, that it's confidence intervals are less misleading. P-values, when people see a small number, they think it's very precise. But we use normal approximation. Actually, the Barry Essen bound doesn't really guarantee us why we can approximate. It's a weak convergence with local mathematics. Where did 10 minus 8 come from? So, but there are problems before we even worry about the approximation. Is we quickly assume a probability structure when there's uncertainty. When there's uncertainty, it doesn't mean your particular analytical probability model is the right way to go. It's not any time you have randomness, it should be probabilistic. Why don't you do fuzzy logic? Also entertains some uncertainty, right? We make a huge jump. Oh, there's something I know, let's do an analytical structure. It's like we have a crack on the foundation. I just realized a couple of years ago that I have been doing for many decades. When you write a big X random variable, it's assumption, which actually, I realized that now after I got into causal inference, this counterfactual somehow made me think harder. Because if you have only one data set, and that's the only thing you care about, you don't need a random variable. You at least need another realization, which could have been observed under the same distribution for you to really go there to entertain the notion of probability distribution. If you assume there's another realization which is realizable, then you assume there are physical conditions, they're similar enough that you can put them together. So that's stability assumption. So even random variable is assumption. And I definitely have done that for years. Big first class, big X. Now I don't introduce random variable until third way through the applied statistics class. Just do prediction to see how you validate it, and then introduce probability notion to statistics very, very carefully. If you have explicit randomization like randomized experiments, yeah, but that's pseudo number generation too, right? So you don't have exactly randomness, and that you have photon emitted from a radioactive material or something, right? Because that pseudo number is deterministic. And if you don't have your assumptions substantiated, where does the p-value come from? What's the sample space? We use probability distribution. We don't think about the sample space. This is the first thing we teach in probability class. It's the sample space. When you think about the sample space, you think about other data could have been observed and wonder what the condition, why you can put them together. And also, small p-value often measure model bias. Your model is wrong, and your p-value is very, very small. So I start doing more in my class, mis-specified model calculations instead of the ideal model. We tend to have this problem of illusion, which is use the word true model. And later you have to tell the student true model is actually not true. I think we should move away from using the word true model in modeling. We should use approximate or postulated and talk about evidence. Because if it's true, why do you need to any evidence? It's already claimed to be true. There's no need to back it up. That really, I mean, the experienced people, of course, know that, but it's just such a bad way of introduce somebody. And later you have to tell them, actually, you shouldn't use true. So I think we should just move away. I still slip in my class and use true model because we have been brainwashed to use true model. The word has a meaning, right? Words can be weapons, right? When you think true, you think true. Of course, we're in post-truth era now, so everything is different. So we need trustworthy measure of quantitative interest. And over multiple probability models or without probability models, including data cleaning. So what we propose, you have a series problem formulation in the documentation, and you specify target of interest. You can also seek stability across different models and different formulations, different data intake. Seriously, we don't have any diagnosis anymore in statistical inference. That's where my question came from for a previous talk. We need to at least use prediction screening for reliability check. I was horrified in a qualified exam that a student presenting from, I think, modeling some hydrology problem, time series data, and he set up a hypothesis testing problem by scramble the data, basically made it IID, and he rejected that hypothesis, and he said his model was true, basically accepted. So he basically rejected the data is not independent. There's no evidence why his particular time series model fit the data. The thing is, if we don't have prediction screening, we can make up this really strong man, very unrealistic non-hypothesis and reject that. The Neyman Pearson framework kind of allow you to accept the alternative, which can be equally bad, away from the truth. But if you take the Fisherian approach, which I like better, which is for each hypothesis, you have evidence of p-value, if you can calculate that right as evidence instead of choosing between two. That's really problematic. I think if you look at how Neyman developed them and Pearson, probably they have the idea that the non-hypothesis is established scientific theory. And that's okay if you do that, do the Neyman Pearson. It's only now people make up all kind of crazy non-hypotheses from nowhere and reject that has no value. But if you use Neyman Pearson, it allows that. It's not that originally they planned, but that's how people use it. Scramble the data, and usually, I don't know what hypothesis you tested. You have some reference distribution. So you should at least do reality check before you go to inference. And then you have a target distribution, target value distribution, taking into account appropriate data perturbation. It can be data cleaning. You might have two versions. You should calculate the same value and see how different they are, and put it together under the perturbation distribution and report the perturbation interval. And I won't have time. We also have a hypothesis part. So for us in the PCS, hypothesis testing through data perturbation is a constrained data perturbation taking into account about the non-hypothesis. So first you think about what it means about the hypothesis with the data. So if the student actually did that, he went there, I'm really in my non-distribution assuming my data is IID, that's not what I want to test, right? So framing matters. Then right now, non-hypotheses are now created equal. Some are meaningful, some are not, but we're not saying which is which. People just do all kinds of non-hypothesis testing, which often don't make sense. So we did a very basic simulation study to compare what we care about is about ordering of important features. This is simulated under 6 different models. 5 are misspecified with heterogeneity and missing linear predictors and nonlinear Boolean function as the true response function. We compared our three things. One is our PCS, use ESCV basically, and then the selection inference from the Stanford group. Actually, the code was not easy to run, but it's solving a different problem. They want to control FDR. Here, we want to order things. And then just the good old asymptotic normal approximation. You do the source selection and just do normal approximation. Pretend there's no selection. Actually, it doesn't work too badly. That's the green for below 10. And actually, post-selection inference doesn't work very well. This is misspecified model. This is the true model. But even for true models, under the right ideal models, you can see I keep using the true model. And selection inference also has a problem. So our red overall works pretty well. And that's the collaboration I'm engaged. The biologists don't want me to tell them 1%, 2% cut. They have money for certain experiments. So they said, I want you to actually work on getting better statistics for me, not tell me where to cut. Because I have money, I know where to cut. So this is something I think very important, and it's also very transferable. You take random forest, or iterative random forest, and lasso. They're both going to rank the importance with metrics. And the ordering can be aggregated or compared, but not the p-values. I don't want to compare p-value from random forest with a p-value from least square, from linear model. It just doesn't feel right. They're not postulating similar probability models. Actually, we can say that the climate scientists are already doing that. They're considering the team variation And we're now just going to look at this one, like 1.5. We can look at both. So you have a range of 1.5, 5.5. So we know now that I think this prediction probably was made earlier. Then we are now definitely there. We're probably higher. So this is a perturbation interval allowed legitimately under PCI inference. It's expansion on traditional statistical inference. And this is a global mean temperature change. I should explain. This is multiple teams. So interpretation, so now we're giving an interval. We can incorporate the multiple models into the same perturbation interval. But how about interpretation? Sometimes you cannot quite put them together into an interval in high dimensions. So we also have the second part of the neuroscience project with Jack's lab. This has been going on since 2013, and the paper is still being written. Jack wants to write a paper that can be read 100 years from now. So he's going through the paper line by line with my students, and my students actually now enjoying it because he's really spending time with them and not worrying about, and he said, I'll be the next. So he's going to train me how to write a scientific paper. He's a very, very good writer, but he just really rigorous about what we write, the meaning of the words. So the project was led by my two former students because it has been going on. He just joined UCSF, being actually direct neuroscience analytics, and Yuan Sichen now in ETH doing a postdoc. He will join Duke as assistant professor. Adam went to Google. Mike now is at Allen Institute for Brain Science, and Ben collected data, was a postdoc in Jack's lab. He's at Oxford right now. It took Ben 2 years to collect this data, so it's very expensive data. The data really, they had some small publication, but nothing really the data hasn't been really analyzed. So back to the brain. I said V1 we talked about, which a Cabal Transform. And we did a movie reconstruction basically using V1, V2 data. We had V4 data we didn't use because we didn't have a good forward model. It's a very difficult, elusive area. Actually, Jack's postdoc work was on V4, very little work. It's not IT. IT is object recognition. This is more complex shape, but not exactly. At the same time, we have huge interest by various people on deep learning. It's hyped, but there's also something there. It's not just hype. There's a lot of instability issues we need to solve, and you can have ImageNet, big data. The first layer you learned is very much like Cabal-like or V1-like. So here actually can be replaced. Stefan Mallet have been trying to use something called scattering transform to make a lot of the step as mathematical transform. But it's not enough. Scattering transform is not enough. You have to do other data adaptive learning. So those are the data. Remember the cat was probed by different bars for edge detectors. And people have been using very complicated synthetic shapes and hope V4 neuron will get excited. So they just make up these things and see what happens. So it's not very efficient. What if you cannot think of a shape a V4 neuron cares about? You just miss it. So we want to learn from the data for the design. So two things we set ourselves to do. We want to characterize neuron in the sense of Hubble and Whistle. And we also want to see does a convolution network really capture anything about brain function. We actually have positive evidence for this. Actually, it does. So we were doing some 2 layers of deep learning, dictionary learning. And then I gave a talk. Joshua Banjo was speaking after me 3 or 4 years ago. He was doing deep learning. So we said, let's try deep learning and see what happens. And the results surprised me. That's when we jump into deep learning. So we can replace a lot of our human hard work by this learned. So this is AlexNet, learned from ImageNet, like 1.2 million images, public data. And we just take our image, which has nothing to do with the ImageNet, black and white. We make 3 channels the same. And we're just going to put it through. Take this as fish extraction. trained on human data. So in 3 different senses, we're doing transfer learning. Color image, black and white. This is very high level task by human. This is primate, macaque. And this is for neuron activity. We have single neuron, not fMRI anymore. And we do the feature extraction just like the last project. And we do simple linear regression, the sewer ridge. And we got the result that slightly better than 2 of my best people work for 2 years using 2 layers of dictionary learning. So that's why I jump into deep learning. Right, we already did work. And this is just replace a lot of our human work. But of course, this is learning on big data. So I have to believe that there's something about primate cortex, the first few layers, really captured quite a bit of human vision. And that's why medical imaging now using deep learning too, is because the early layers is kind of replacement, a surrogate for human brain, and radiologists basically use their brain. Right, and then you tune it, and we tune it here to a particular application. So then we have a problem. We can take AlexNet, the first 2 layers, we can take 3 layers, we can take 4 layers, we can take 5 layers. We stop at 4. So we have 3 models. And we have Ridge and Lasso, we multiply, we have 6 models. We have GoogleNet, we have VGG, we haven't gone to ResNet or the newer ones. So we end up with 18 models. Correlation between the predictions, 0.92. They basically very similar predictions. And how we're going to do neuroscience with it. It took us a while to know what to do. And we decided to invoke, oh, of course, I do it again, stability. And we designed, pull the 18 model together at a value like deep dream, or we call deep tune. And we come out with images like that. So this is like replacement of Gabor, data-driven. We say this neuron seem to care about shapes like this. It's a curvature neuron. But then we discover that the spacing between is an artifact of particular neuron. This is from AlexNet, and probably we have to chop it into different pieces before we try. But compare with the previous synthetic stimuli, this is more naturalistic, and also this is just take humans to design and try, right? Shoot in the dark and hope this neuron cares about what design. This is, we observe something, we can suggest. And then Jack stopped doing physiology, so we couldn't do the experiment. But a top neuroscience lab from MIT, DiCarlo's lab did that. They have their own version of it. We're on parallel paths. And with a science paper earlier this year that they show feasibility. So this can be a closed loop. So while you observe data, you generate these deep tune images, and you put it back and get verified. So it's hypothesis generation. Okay, so that's most our work. I want to return to the connection to economics. So one question you're sitting here is that, is PCS firmly relevant to economic research? I would like to think that it's yes, and let me try to make a case why through this work grows in a time of debt. Wow, that's great. Yeah. So this is the main figure in that paper. They made judgment calls, right? And let's look at, so on this side you have the GDP growth, this is inflation, and here you have the debt GDP ratio, below 30, this is mean, this is median. So they classified or categorized country and year. So each year, each country become a data unit. And they look at their growth below 30%, they put into this group. Between 30 to 60, oh, this is below 30. 30 to 60, this group, 60 to 90, and anything above 90 into this group. But they seem to have did some unconventional weighting in the sense they didn't treat each country same way. They kind of averaged over country and then For each country, they got a number and an average equally for each country. So some country has more years than others. So they're not treating country year as equally unit. So that's what's pointed out by the later paper. Okay, whatever. So that's what they did. The result is not too different if you do a little differently. But it's really weird to connect a median, average and median. If you look at these things, they kind of run together. But you should really do this with this and this and this. So the average went down to minus 0.1%. So when New Zealand brings back on, this goes up. So it's a weird graph in the sense that why can't you do this as almost like something comparable? This is comparable to that, and this is to that, and that. Because one is mean, one is median. So if I take a PCS critique, already pointed out in the literature, the data unit removal was problematic. There was no documentation. They should have explained why they removed New Zealand. And there was coding error. I didn't look into that. There's coding error there too. So, judgment call. When this follow-up paper or critique corrected, brought New Zealand back, went to 2.2%. It's also the interpretation. But I was asking more questions. I did it on the plane. The economists can help me here. Are the debt and GDP ratios comparable? They also look at they talk about over 200 years as if they were comparable. They only did it the data they plotted was from 1946 after the war and to 2000 and something. But they talk about 200 years. I would be very surprised that the calculation the same. Can they be made comparable? I think principal comparability is like the mean and median, that's the same problem. You shouldn't put things in the same plot when they are not comparable. My other question is time series dependence. They treated the country and year as if they are exchangeable, but there's time dependence. I would like to see the different country plots and all of that before I reach a conclusion. So that was pointed out. They didn't deal with it, but they pointed out as a problem. And they also have I showed you the advanced economies, and also there was a section I won't talk about, emerging markets. Are these choices standard? I would like to remove a few countries from the advanced economies and see whether everything will stay the same. That's another form of perturbation, even we don't deal with the time dependence, right? Definitely removing New Zealand, we know it's not quite stable. They didn't completely remove New Zealand, but part of New Zealand. So I would conjecture that probably things are not exactly stable. So how do you define advanced economies? Right? You should write a documentation about it and to argue or do some perturbation to see the conclusion doesn't rest on your choice of advanced economies. And also, if you just look at the mean and median, for the last bit, very different. You already know something's not quite. They should dig into it. Maybe discovered it's very sensitive to what country it is, right? Mean and median are quite different. One is negative, one is positive. That's already say something the data has some very dominant outliers. You could just dig that. This is a perturbation analysis, two methods, very simple ones, mean and median. That means there's instability. Which one do you take? They took the mean. A lot of people took the mean because that means austerity policy. And also histograms. You want to see the variability, which was done in different way in the follow-up paper, right? You want to construct a perturbation interval with all of that, and whether you still have negative or not. And they kind of assume causality from public debt to growth. It's like, if you have this association, that means you should do something. And all the politicians definitely love that. They, how do you translate this association into action-warranted policy change? At least I will want to see stability analysis here to collect more evidence before I even talk about causality. And the politicians love to interpret the people, I think, already believe in austerity. That's what humans do. They look for evidence to support what they want to believe. and possibly there was a negative impact of this paper. So it was quoted in the New Yorker article that you guys probably know him better, an important figure said the latest, in his speech, he cited them by name, and then he said the latest research said that once that reaches more than about 90% GDP, the risk of large negative impact on long-term growth become highly significant, right? He's adding all of these things, which I don't think there was hypothesis testing in the original paper. So let's look at what's going on. This is the original. I have to shrink it to the scale of the later paper, right? So there's huge variability. If you look at this, you don't see it. And over 90%, all of this got grouped into these blocks, right? Actually, even you do 90%, you still have, after the data correction, 2.2. They emphasize the lower instead of saying actually still positive. Because 2.2 during a recession, after recession, is not too bad. But the abstract interpretation emphasized lower without saying, they had a disagreement, right, between the mean and median. So they start emphasizing the lower, which is the consistent interpretation, but now knowing that this number is questionable. Right, so all of this, if you do this plot as the later paper, even ignore time dependence, you have much better view of what's going on. Right? People look at this, it's our nature. We imagine everybody's doing something like that. We cannot imagine variability based on the mean. They are independent. Right, so they should have at least do a box plot or something there, and then have the center and with mean and median on the same plot and draw two separate lines connecting the median and connecting the mean. So that's the critique of very simple but very impactful paper. So I think for one thing, if they follow the PCS documentation would have helped. A lot of the questions they will probably reflect themselves and do the perturbations, and then they will have seen things which the later paper kind of brought back. It's document what you have done. And even for a new group member, right, we definitely have a recent incidence of the original data was a small human study about some deep learning interpretation method. Couldn't find it anymore, right? We only had a summary statistic, right? Just was like last year. Right, so documentation is very important, data, original data, and all of that. So here's a summary. We tried work towards vertical data science, which is a big goal, but I think we should try to do that through the PCS framework. We want documentation on GitHub. We want a responsible, reliable, reproducible, and transparent data science lifecycle, so reach trustworthy data conclusions. And the inference take into account data and model and researcher perturbations, if we want, or versions of you. Data perturbation include data cleaning, and we have 2 case studies. As I started, I want to emphasize the importance of domain knowledge. Of course, good domain knowledge help, bad domain knowledge won't. And PCS also can generate testable hypotheses towards causality. It's not causality, we have been relying on experiments in my lab, but it's better than just association. So we should talk about strengths of causality instead of causality, no causality. And the next steps for us, we want to really develop further the PCS inference with different model classes. We're trying that out on 2 projects. Basically, we're doing some epistasis discovery with the UK Biobank data. And depends on which model you use, you get different conclusions. So we need to reconcile that. And we're also doing a cancer drug discovery project with Mayo Clinic. Again, if you use random forest, actually, somebody asked a good question. E2 random forest can be viewed as a sparse seeking model selection for nonlinear interactions. So it can be, it's just like lasso can be used for other areas. But you do want to think about whether this thresholding behavior might make sense for your problem. And we're also doing PCS with causal inference with continuous drive data. We try to bring in prediction as model checking in that particular problem. Again, there we work with David Madigan and my group on some impact of a particular painkiller on some GI event. That depends on what the model you use, you might have very different qualitative conclusions based on age. Depends on whether you put a quadratic term to your logistic regression or not. So things like that needs to be discussed. And we try to team up. I gave a talk at the AI meeting at UC, and the ER doctor approached me, so we try to disseminate the PCS framework with a case study to emergency medicine. So a lot of the young doctors are actually very impressive. They become very computational. I'm working with another one with UCSF, also a young doctor who's doing a lot of good quantitative work. And we also talked about with a scientist, social scientist, to unpack PCS with social science examples, and working on a book. And we're also working on theory and fast algorithm because stability really adds a lot of computation. You really have to kind of couple them together, otherwise it's going to kill you very quickly. And a friend wrote, also a research associate, Radek from Berkeley, got really excited about PCS. He wants to build a computing platform, and so that people can really use more easily than everybody have to teach. A lot of the stuff are kind of repetitive, so we should have a platform that other people can more easily plug in. And I hope some of you will join us. So the last point I want to make is that people are actually the center. I'd like to thank my group. Like, we do pretty slow research, and they still join me, so I'm very privileged to have these young people who want to do serious research without worrying about publications. Not completely, but we try. So people are at the center, and we do relevant theory. We want critical thinking. That's what I try to teach in my class and also for my book. And you have all these problems, and you want humanly understandable conclusions. So if I look at the data science community, within the community, I think we need not just transdiscipline, we need transmethodological people. We need people who work on more than one method, so we remove the person-to-person versions of you. You love lasso this phase, next phase you do random forest, and you get different conclusions. So we need trans-methodological people. We also, maybe you guys doing already, in the States, not all statistics department like that, still kind of star-shaped, more mathematical type. We need to go to group meetings and subgroups, work more as collaborative team. That's why I can have so many people. If I do one-on-one, it's impossible. And they also learn so much from each other, and they teach me. Also, we need to have topic-driven groups. New topics, like there's a new ASA text analysis section. We also need to write vision papers to help disseminate our consensus to outside and for young people. So for V4, my group, when we got on the project, really benefited from a 2012 paper. 8 leading V4 experts wrote a review paper. So we just read that and went to other papers. Instead of we struggle, find out what happened with V4. We don't do enough. We don't write vision papers, position papers. And as I mentioned yesterday, you need to embed student postdocs in the lab. So Tukey said something like, with statisticians, we could play in everybody's backyard. I'd like us to play in the front yard. Because a lot of the data, biologists, it's pretty new for them. It's not like they have intrinsic understanding of data, some like South Block, like they work for years. So we have a role to play. And a lot of them, the younger biologists are quite quantitative. So also the question to us. So the young generation biologists grow up being quantitative. Like Jack's lab is very computational. When I started working with them, I was very, very impressed. Neuroscientists building their own computer, they were buying chips because it was cheaper. Right? So they don't say that's not neuroscience. But they're very quantitative. So what do we have? We don't have science, we only know quantitative modeling. We're not going to be very helpful. And our facing, I do think that we need a few common, robust, reliable products. We need to really understand, like deep learning has the hype, but also they try to understand it. Something got wrong, other people discard because there's a concentration of study of deep learning now with platforms. We need to make random forest like that, or lasso like that. We have maybe 100 variants on lasso. I think we should just understand the vanilla lasso and understand where things fall, where things work. Like, there's a huge community in applied math. They just do SVD, and we all benefit from it. Where's our SVD? The whole community, you can do your own pet projects, but we need to put our sources together to have something, somebody coming from outside, this is robust method. I know if it doesn't work, this is a warning label. We need a few, otherwise the computer and the scientists are doing our work. What do we offer? And we also need certification labels for open source and safe software. As I said, I hope I don't get killed by my own algorithm, but I don't even know how to make my algorithm safe. Somebody else had to take a look. We need rigorous evaluation process and new algorithm, and we want to build modularity. You want certain parts people already understand, instead of everything from scratch. It's just very hard to evaluate and for other people to learn to trust. There's something called red tagging in software development. I think we need to do that. And there's also something called a risk officer. I learned at the meeting, the Trustworthy AI. At Capital One, they have something called risk officer. It's that the most senior experienced data scientists critique and take apart the models they develop. I feel like I'm a risk officer as advisor. That's usually my role. I tell my students that you can be in love with your algorithm like a brainchild, and then you should be your worst enemy to take it apart. When the whole group cannot take it apart, we're in a good place. It doesn't mean it's 100%, but it's a lot better than without the red tagging process. But a lot of the publications, I don't know about economics, in statistics, are in the in-love phase. They never gone through the critique phase. And the referee, if they're responsible, become the risk officer. But that's too much for the referee. That's the last stop. You should do it yourself, and then referee do the last stop. And it's kind of scary. I hear that NERSP, or the NIPS, they now have undergraduate as referees because the volume of papers exceed human capacity to referee. And we have to solve that problem. So here's a call for the leaders here. Academic, industry, government leadership, and funding agencies need to incentivize quality research. Forget about trustworthy, responsible AI if we don't have trustworthy, responsible publication. That's where we communicate. If we don't start from there, where are we going to have trustworthy AI or trustworthy data science? I think we should stop paper counting. But we need to emphasize, I think Europe is better than the US. And we really need to form team brain because the problem is just so complex. One brain doesn't solve it. You need a team brain. But for a team brain, you need a fair collaborative environment so the credits are distributed fairly so that the best argument wins, not because your position, your gender, or your ethnic group, or anything else like that. Right? You want to have an environment people can voice the ideas and have a way to reach consensus. So our papers, there's a paper I took out actually last night. It's on interval machine learning, just didn't quite fit. So I hope you will take a look. It just appeared in PNS. Our PCS paper is the final stage of PNS. And this is really try to define important metrics for evaluation selection, predictive accuracy, descriptive accuracy, and relevance to a human population to a particular problem. You cannot call by interpretation without a human audience. A doctor explained an algorithm to me is very different from a random person on the street. I happen to work on statistical machine learning. So we call PDR. And I want to have a shout out for the Berkeley Data Science Initiative, which I talked to yesterday. For the ones who didn't hear, we have a new associate provost, Jennifer Chase, and we have doing these really wonderful classes. Joined with CS, which also this one has a domain component. And this is hugely successful. We have a lot of the freshmen go to Data 8 and creating a community of teachers from undergraduate. We don't have enough graduate students to power this. So each class have like 100 undergraduate teaching assistants. Actually, my daughter is one of them, so I know also from a parent point of view. that really we graduated 100 data science majors already, and what the students spoke really also changed their life. It's a big public university, so that it's like a club. People work on data science. And our organization vision, some of you might, it's from 2016. It was 105 page about why the intellectual vision, the three components, drove the organization change. So under Jennifer, we'll have a quantum state. So statistics and EECS stay as a department. We belong to two deans, the new dean and the old physical science dean. And our physical science dean is a physicist, so she gave the name of quantum state. So we are in a quantum state. It's kind of nice because university is too hierarchical, we don't have crosstalk. The dean, our chair have to go to both meetings and then cross. And a lot of the data science positions are coordinated and can go through one dean and the other. So the book, we really want to, is for upper undergraduate level, beginning PhD, for people who older want to learn about data science. We want to bring the basic principles. And so you can use your common sense before you drill down to the details. And for the leadership, you can understand the principle and ask questions already without understanding the details. So all this data science life cycle stops will help. Thank you. I have to say that the concert was the best part for me. Thank you. So much talent. I have a suggestion. New future hires have to play a music instrument and can sing. I was very impressed.
What a wonderful lecture. Thank you so
Thank
much.
you.
We have time for questions. We are on time. Don't be shy.
Yes. Young people, right? You should.
I can speak like this if you hear me.
On its way, on its way.
It was just a curiosity on, thank you for your talk. It was
Thank you.
very interesting. I just had one question on CNN, because at some point you talked
On what?
on CNN.
CNN, okay.
You talked about the fact that applying CNN, you got better results than 2 years of work,
Yeah.
or your best people on images.
Yeah.
And then you also mentioned medical applications and medical imaging applications. But my question on that is, how about explainability in that sense? Can you actually translate those methods in domains in which explainability is quite essential? How would you address that, and do you think is an issue in those
So
techniques?
for the stability, we did 18 different models, right? So, and then we're also going to add stability. We're going to take different parts of the image, not just the whole global image. So that's also introduced at the closed loop experiments phase on stability to find out which part this neuron care about. So the neuroscience application is less mission critical. We've got something wrong, but we still help the scientists to narrow down the design space. But for medical applications, I think the robustness and transport learning, we have to make progress. And we also have to understand under some idealized condition how neural nets work, so that's the theory bit. Right, the neuroscience theory people now have been saying that, oh, we don't have variance and bias trade-off anymore because you get training error being zero. But I think there the confusion is because people are not capturing the complexity. So we have a project try to capture the complexity, and we believe that if you have the right measure, better measure of complexity, you remove that the double descent. So I think theory now is really critical to help understand, and we should also do lots of experiments to break the method. So because the medical application, the time is very short. Oh, we should take a very prudent approach to put it on the clinician desk. So I talked to a friend from China actually, and he worked with medical imaging, And he said the doctors he works with in China don't want to use it yet. They don't feel safe. So that's a nice pushback. So I really think that we have to be very, very careful when we move to the medical domain. And I'm glad the doctors. So, but interesting, this emergency room doctor, Aaron from UCSF, I work with, so he did a draft of the paper. He definitely, we're going to revise, he definitely showed a lot more positive optimism about machine learning with what he wrote, because they're now trained in that a lot of outside for business marketing, there's a huge, it's like magic. So we have to help to bring that down. And the best is actually talk to the doctors directly. Good doctors, I think, naturally worried. I hope they provide some good pushback. With Google Health, I hope they also will really vet what they do very carefully, but I don't know where they are regarding that. But there are definitely conferences on trustworthy AI, so I think the AI community is being aware, and my colleague Stuart Russell has a book called Human Compatible. So I got a copy, I haven't read it. His idea is that we cannot wait until disaster happens to worry about AI stability or AI trustworthiness. And so basically in the US, I think it's more or less consensus now. The future of AI is human-machine collaboration or human-augmented AI. I wrote a little article called Statistics in AI 2018. So the main message is that we need a human-machine collaboration. But I think the industry is pushing something. I mean, about autonomous driving, right? They hyped it, but already there are smaller companies, already people saying that they use a lot of people in, say, India to help the drivers to drive, right? And the big companies didn't talk about it. And if I talk to the young people in the valley, they really, the autonomous driving cars become very specialized. So this friend of mine work for a company, they're going to deliver grocery to your house. How are they going to learn by your house? They send a car with a person, drive 10 times to learn your house. If you're a new resident, they're going to take a while before they can serve. So it's very, very narrower than this free driving. Imagine driving with Italian drivers, right? With your reputation, it's not that easy to navigate. Would you stop? Or in Beijing, right? People cross the road. You know, I don't see that happening, but for very narrow tasks, I think it's possible. That's where the value companies are moving there. They're kind of giving away this grand vision. That's a long answer. I don't know. I address your question. Yeah.
Question there, third row. Please signal your intention to ask a question so I can get the mic to you quickly. Daniel.
Thank you very much. A question of something on a topic that I'm working on lately, which is, okay, I understood that at a certain point you got like 18 models that you test, and you got a very high degree of correlation. That was a sign of good stability, right? Let's imagine now that you can't achieve that degree of correlation when you test several models.
You can achieve what?
That you can't reach that degree of correlation between predictions. Could it be like a model aggregation algorithm, a possible way to recover stability in that case?
Yes or no. I think random forests already have data aggregation, but it was not enough. It helps. So we had to add extra layer stability to get iterative random forest.
Okay.
So it's like how much stability and aggregation you add. So it depends on the problem. So in general, there's always more to be added. So we're learning. So ideally, we understand like, I'm pushing this stability. We can have categories and website. People say this type of problem, this type of the stability work for your problem. So when you put up a software, you have 10 simulation scenarios based on real data. Basically, you have some reality in your data about the X design or the form, and say that here are the scenarios, we have different performances. And you can see the user say, oh, this is more like my problem, and documentation. help people to. You need a manual, right? When I get a furniture home, I have a manual how to use it. But we don't have any manual except here's a bunch of line codes. We have to go there. Otherwise, anybody can grab your algorithm and my algorithm and do things we don't want them to do. So it's the downside of open source, which is great sharing, but it's also quality control. So you have to balance.
Next question.
So first of all, thank you for your insightful talk. I have a very general question. You insisted a lot on the issue of stability, but what do you mean exactly about that? It's a very general term. So maybe it's about instability of language, but it's. I was wondering whether you are more concerned about the fact that the distributions of observations are uniformly distributed, or they are identically distributed across different setups, or it's more about independence of observations?
That's a very good question. So at the heart of the stability is really a lot of let the user define and through documentation. So basically, you define your perturbation and you argue in a document why that's appropriate, and you evaluate that. So it can be any of the things you said. And I give the user the power to do that, but I'm saying that these are the issues I want you to consider. And you choose, and you make a case in the documentation.
But you see the issue, the condition, the
data cleaning is a big concern for me.
As a sufficient condition or a necessary condition for prediction? In other words, in your view, is there any sufficient condition for prediction?
Well, prediction is required in PCS. So that's the first thing before you worry about stability. You want some sense you have reality. And on top of that, you want to worry about stability going for inference. And I don't think you can ever say in the broad terms what's sufficient. It's really, do you convince yourself as a professional that this is good enough, the bar for your group? And then for your collaborators and for decision makers who are going to use your, for medical, I'm going to raise the bar very high. Right, so for one of my first scientific paper appeared 2016, we had 6 pages of paper, we had 45 pages of supplement material because I was just going through all the things I could think of. And we even did a knockout experiment, but we couldn't analyze it. So it's for Drosophila, right? It's not like anybody's life, but it's science, right? You want things to stay there, people can use it. So we have a follow-up project with the Allen Institute, use the same methodology, stability-driven non-negative macrophagocytation. It's kind of like first layer of deep learning with positive constraint to try on another genomic data. So that's another thing I feel like we need to persistently, even beyond one paper, to understand the methodology come from your group. Because we do have problems, students need to graduate 5-6 years, you cannot keep them longer than that, or they don't want to. But something like all these 9 climate models, group of people work for decades. So I think for the robust, shared methods, we need to do that. More than one group, but also for multiple papers, even from the same group. So in that sense, it's never sufficient in your way. Yeah.
My question is about the data cleaning part of your...
Can you speak louder?
Yeah, sorry. My question is about the data cleaning part of your, flux for veridical data science.
You mean this
Exactly. So in the data cleaning step, you often have many choices.
I cannot hear.
Should I keep it...
Oh, the data cleaning of the data.
Should I keep it closer? I don't know. So how do you, so because you have so many choices and you have many combinations for each choice, it quickly becomes a full factorial design with just so many options. And if you really want to explore all combinations of choices at the data cleaning stage, it becomes quickly intractable. Now, in sensitivity analysis, they have a way to deal with that, so like simplify, just looking at a few interactions. So my question is if you think there is any similar way to deal with that in the data science side.
I would say for data cleaning to be realistic, at least you should try the 2 standard ones. Try 2. Right, that's a start. And we haven't really gone there either, right? My students do 1 data cleaning and we do it. So that's what I'm trying to do in my group. At least do 2. That's a start. But you're right, that's why there's also computation overhead when you tried all the different ones. So that's why I want to build a platform to make that step easier. But you still need computation power to do that. So in general, just like, do you want to spend more time? For me, it's like a lot of time people gain a little bit percentage increase for particular data they have. I don't think it's worth it. I'd rather people worry about stability and go for different new source of data. So for one project, we're working with UC Davis on prediction of surgery site infection. We're using all the data from UC Davis, and we're going to have Davis VA veteran hospital data as our transfer learning kind of validation. So I like to think our data science project as a continuous investigation. And we do have to put some stops at paper publication, but if you really want something to be deployed, I think you need to continuously work on it and validate it. Just like, you know, for software, right? They keep rolling out different versions. I think we need to get into that mindset for some standard things a lot of people can use. So there's no quick, I'll say, concise answer to that. And this is really kind of a call to arms for people engaged, and maybe in 10 years we can answer that question. It's more sharing what I think where we should go.
I wanted to try and ask a question, trying to link 2 notions here. So we need to perturb to try and assess stability. This has a computational cost. How to define perturbations? You were raising the issue. It's very, very critical, because you can probably not explore all possible avenues of perturbation. You have to make some choices. What are the important directions to perturb data? One point that I wanted to iterate, because I'm not sure if it got registered, this notion of essentially building simulations around actual data so that you can respect some of its structure while pursuing perturbations. But the question being that I wanted to ask, perturbations can also be used to explain, to try and map what some predictions mean, okay? What is driving them? So for the explainability side of things. And I was wondering if there is a way to essentially build into the same perturbation design stability and explanation and interpretation.
Yeah, that's something I have been thinking about, but I don't have anything firmed up yet, because, I mean, it kind of goes back to the question about causality.
Yeah.
Right, so both papers, we say very briefly, because that's something I haven't thought enough to go out and feel confident about what I'll be saying. So my thoughts are, if you look at huge randomized experiments, which people call as the gold standard, I always had a problem in the sense that I have huge number of covariates. Anytime you do a randomized experiment, they're not going to be balanced on all the different dimensions. So for me, observational study, many of them together, is not necessarily weaker strands of causality than a randomized trial with many factors you don't know which one is relevant. Right, so it's a kind of a notion of what's the strands of causality. I think that's related to explainability or interpretability. But I also always like to embed myself in a particular problem, because I see a lot more things before I even tackle that and generalize. That's just what my preferred approach is. Start with a problem, solve that problem with your eye about a possible generalization. Because in the beginning, when you're not seeing things, the specifics of a problem can really help you. And that's why I want to put myself there. So these are the questions I've been in my mind, but I don't have, I think I agree with you. That's where we could go, but exactly how, I need a perfect problem to think about. Then in general, or you can do perturbation, as you said, right? Randomization, perturbation, especially with pseudo number, it's kind of not as different as you would think. But why it's done two things. The other's post collection. So there's a qualitative difference as well. But can we bring, for me, that's what I said, PCS is closer to causality than just P, but how much closer? And it's also how sensible your perturbation is based on domain knowledge. If you can bring in domain knowledge through the perturbation, you're more powerful. And same with randomized trials, right? To know which ones you look at to control for the possible confounding factors. So that part is very hard to quantify. But with a particular decision to follow, I think we might be able to do something. So I'm looking for a perfect project to think through. So far, the causal inference project I have is either methodological or other people's data. I need to really, if I get a collaborator who is running a clinical trial, I think that will be better than just somebody else's clinical data. That I need humans to kind of to dig into it and to borrow their, talents.
Validation.
Yeah.
A new kind of like in medicine, they are already used to have randomized trials involving also humans. That's so.
Yeah.
I was simply agreeing on this final statement.
Yeah, I mean, I don't know how many of you know that the lung and the smoking connection was declared causal by NIH committee in 1963. So they look at 29 observational studies. It was a committee decision. It was never a physiology experiment or anything. It was a human decision of a committee. And they look at 29 observational studies. And I still have people, my friends, who don't believe that, right? Because the causal link, and Fisher might be right. I think there's some beginning evidence that maybe a small proportion of us, there's a genetic link between smoking and lung cancer. Right, drive both. I'm just saying that a lot of what we believe is a human decision, and we should ready go back and revisit with more evidence. And do you always need intervention to prove causality? Earth and Moon, we never did intervention there. We believe they're connected, right? We believe there's a causal, but maybe the other way around. I'm just saying that somebody said earlier that maybe Michael, that the reason we want to go causality is actually we want to do things. It's the action to follow. If you use a causal language, somehow that's human. We want to do something. I mean, all of us postulate all kinds of causation to justify our actions. Most of them are completely wrong, but make us act. So I think causality should be thought more in terms of action. That's more healthy. And that's what we do, because we conjecture with one data point about why this person does that to me, and we act to that. It could be wrong, but it's just a language we use for action. I think that's probably pragmatic definition of causality. Thank you.
I think we should wrap up the session with a note of regret. I thank you so much for
My pleasure.
this thoughtful and inspiring talk you gave,
Thank you.
and for the lot of work you've clearly put into it. So we genuinely all thank you.
I went to sleep at 2 a.m. yesterday.
Join me again in concluding.
Thank you. It's been my pleasure. Thank you very much.
We'll have plenty more opportunities maybe during the day to exchange views and ask questions. Lunch is served outside. We are on time, and let's try and reconvene on time, 2 o'clock.
2 o'clock, and remember that if you want to hang out and interact, besides the lunch out here,
are open for us to sit down with a paper or...
See you later.